Welcome back. In this lecture, we are going to solve some problems related to partial molar properties. So, let me just start with the first example here. So, for a binary mixture, at temperature T and P, we have been given the change in enthalpy of the mixture in this form, okay, where C is a constant. Now, what is being asked is to obtain the partial molar enthalpies of the two components. Okay, that's question number 1, and the second part is to verify that they satisfy the generic expression E as summation Ni Ei bar. Okay. So, we have to now, so E basically in this case is nothing but H. Okay. So, we have this expression of delta H mix. From there we must find out the partial molar enthalpies and show that this exists, this holds, this particular expression holds. Okay. So, let me first start with the definition of delta H mix. Let us do this exercise. So, we can write delta H mix as H T P N, okay, minus summation Ni and Hi for the pure. Okay. So, with the same temperature and pressure which we have. Now, you can rearrange this expression. We can write that as H as nothing but summation Ni Hi, okay, plus delta H mix. Okay. So, now you have got this expression. Now, what is this? This is for the binary mixture is N1 H1 plus N2 H2, and this I can write as total N multiplied by, since we are using superscript. So, I am going to write this in superscript. Okay. All right. So, now this expression we know, delta H, small delta H mix expression is given to us in this form, okay, C x1 x2 multiplied by RT. So, I am going to plug in this here, x1, so C RT and then x1 and x2. So, what is x1? Right. So, x1 is N1 by N, okay, and similarly x2 is N2 by N, right. So, we are going to make use of that, and here we write simply N1 N2 by N square, right. So, this get cancelled, all right. So, now we have an expression N1 H1 plus N2 H2 plus this part, okay. So, from here we can now get del H by del N1, keeping T P N2 constant, and this will be your H1 bar, okay. So, I take a partial derivative of with this expression with respect to N1, okay, and this is going to be H1, this part, plus, since N2 is constant, so this is going to be 0, right, plus you have CRT Okay. So, this n is nothing but n1 plus n2, right. So, this becomes n1 plus n2 square. So, I will take the differentiation of this term first. So, that will be n2 multiplied by n1 plus n2 minus, I will take a differentiation of this first, which will be just 1, okay, multiplied by n1 times n2. Okay. So, I have this expression now, and then I can rewrite this. If you look at it, this is n2 n1, which will cancel out this. So, what we are going to get is n2 square plus CRT n2 square divided by n1 plus n2 square, and this is nothing but h1 plus CRT x2 square. Okay. Now, this is what we got h1 bar. Now, considering that the expression which we have is symmetric, okay, and thus without deriving h2, I can simply write h2 bar as h2 plus CRT x1 square. Okay. We can derive it, but to cut down the time, I am just writing this expression based on the symmetric expression of delta H mix. This is what we have got the first part of the problem. In order to prove the second part of the problem, I simply write H is equal to Ni Hi bar. Now, we have this expression. So, we can simply check N1 H1 bar plus N2 H2 bar first and see whether this is equal to H. Okay. I will just write down this expression. This is equivalent to N1 H1 plus CRT okay. This I can write like this, N2 H2 plus CRT, this is going to be N1 x2 square plus N2 x1 square. Okay, so this is same expression. So, this will be same plus CRT. I can write x2 as N2 square divided by N1 plus N2 square. So, in the denominator I get this, and then you have N1 multiplied by N2 square plus N2 multiplied by N1 square. Okay. Now, here of course, N1 and N2 are common. So, I can take that out. So, this is going to be N1 H1 plus N2 H2 plus CRT N1 N2 N1 plus N2 divided by N1 plus N2 square. So, what we got expression is N1 H1 plus N2 H2 plus CRT N1 N2 divided by N. Okay. So, this is the expression, and this is exactly the expression what we have here. Okay. This is what we had H. Okay. So, this is exactly the expression what we had. So, we indeed could show that the partial molar properties of enthalpy satisfy the generic expression, okay, of E is equal to summation Ni Ei. Okay. Basically, this exercise is helping us to understand how to make use of the partial molar property. Now, I am going to work on another example which will help us, or which will allow us to make use of Gibbs-Duhem expressions. Okay, and without that it would be difficult to solve a problem. So, this is an example. Again, for a binary mixture, we have been given at T and P, we have been given partial molar property of component 2 as A plus bx1 cube. Okay. And the question is to relate constant A to the molar volume of pure component 2 and obtain expression for V1 bar, okay, and we need to also obtain delta V mix, okay, volume of mixing. So, this is a very simple question given to us, and the only information we have is partial molar volume of component 2. So, how we are going to solve the problem? Now, this is where we have to make use of Gibbs-Duhem expression. So, okay, let me start with the fact that when you put x 1 equal to 0, you have a pure component 2, right. So, V 2 from this expression is nothing but A, but this is for pure component, A is nothing but for pure component 2 and this is nothing but V 2. Okay. Now, what I am going to do is basically make use of Gibbs-Duhem expression. Remember the generalized Gibbs-Duhem expression. So, generalized expression for Gibbs-Duhem relation. So, for any extensive property we know that del E by del T remember that we have done this exercise earlier and this was nothing but Gibbs-Duhem relation. Okay. We can divide by n total number of moles and keep so if we divide by n we get something like this E by n. Okay. So, we can write this as also as del E by del T dt plus del E by del P T P constant, okay, minus summation x I d E I. Okay. For a constant temperature and pressure this is going to be 0 and what we get is the expression summation x I d I bar. So, for the case of volume this will be your x I d V I bar. Okay. For binary mixture this is going to be d 1 okay. Now, if you take a derivative with respect to x 1 then you can show that this is nothing but in general actually I can write it, but let me just write it for volume. Okay. So, we have this general expression for the binary mixture where we have connected this composition and partial molar volume properties. Okay. So, we are going to make use of this expression. So, we can actually replace E by anything, E by H, U, G and so forth. So, in this case since our interest is volume we have replaced E by V. So, this is our expression. Now, from here I can now start deriving this. So, this is so let us say what is your deal by dx 1 at T p. Okay. This is nothing but if you look at the expression V 1 this one. So, this is nothing but minus x 2 by x 1 del V 2 by del x 1. Okay. We know del V 2, del V 2 is a plus b x 1 cube. So, now we can take the derivative, this is minus of this and this going to be b x 1 cube, right. I can rewrite this, take the differentiation here minus 1 minus x 1 and this is nothing but 3 b x 1 square. Okay. So, x 1 get cancelled and I have the expression now as 3 b x 1 square minus x 1. Okay. So, this is the expression for this one. Okay. Now, I can integrate this. Okay, I can integrate this and I can get as 3b x1 square minus x1 dx1, and this is nothing but b x1 cube minus 3x1 square by 2 plus c, some constant c. Okay. So, how do you obtain this constant of integration? We know that for x1 equal to 1, V1 bar is going to be molar volume of component 1. Okay. So, in that case, if I plug in x1 equal to 1, what you get? This is going to be b 1 minus 3 by 2 plus c, this is minus b by 2 plus c. Okay. This essentially means c is nothing but V1 plus b by 2. Okay. And remember that b, we have b is a part of the expression here. Once I have this constant c, I can get the expression of V1 bar is b x1 cube minus 3 x1 square by 2 plus this value V1 plus b by 2. I can rearrange and I can get this expression okay. So, this is x here. Okay. So, this is my partial molar volume okay, expression. So, this is what we wanted to find, right. The second part of the question was to find out delta V mix. Okay. And this is nothing but V minus summation Ni Vi, right. So, if I divide by if I divide by total moles, I can get so first let me just write this V as simply Ni Vi bar, which we know, minus Ni Vi. Now, what I am interested is I am interested in dividing it by total, okay, making this as a small, makes this is going to be xi Vi bar and this is going to be xi V1 Vi. Okay. Since this is binary mixture, I can get x1 V1 bar minus V1 plus x2 V2 bar minus V2. So, this I can rearrange because this is only x1, this will be x1 V1 plus x2 V2, this will be x1 small V1 plus x2 small V2. Okay. Now, this expression we have already, okay, V1 minus this part is nothing but b times this expression, okay, and this term V2 minus V2 is nothing but because small V2 is nothing but a. Okay. So, this is nothing but a plus b x1 cube minus a, and this is nothing but x1 times b x cube minus 3 x1 square plus 2 plus half. Okay. So, if you rearrange this expression, so without going into details, you can obtain this as after a couple of steps as b times x1 x2 divided by 2 1 plus x1. Okay. Okay. So, this is how we have made use of Gibbs-Duhem expression in order to solve a simple problem. We obtained for given partial molar volume for component 2, we have obtained that for component 1 as well as delta V mix, considering the constraints which by which we can exploit these expressions and information. Okay, so with this I will stop here. We will continue this exercise, but with a different examples, particularly how to extract partial molar properties from experimental data. Okay. So, yeah, so we will see you next time.